My name is Vince Cerf. I'm Vice President and Chief Internet Evangelist at Google. But for purposes of this video, I'm a member of the Interplanetary Network Special Interest Group Board of Directors, and I'm also a big proponent of expanding the Internet to run across the solar system. And my very good friend David Israel has been very much involved in the whole idea of return to the moon, the LunaNet concept, building Internet in space. But he has an even more interesting presentation to make today, which is all about Ernie the cat goes into space. I'm sure all of you are well aware that the Internet originally was designed just to distribute cat videos all over the world. And as David will tell you, we're managing to get off the planet with this same phenomenon. What's really important about all of this is the technology that allows us to transmit data at increasingly high rates at solar system distances is becoming a reality. And some of that, I'm sure David will describe for you. It's very important that we push in this direction because the data links that we've been using for the last 40 plus years tended to be relatively low-speed radio-based links. But with optical communications, we can get up to much higher speeds, and therefore more data can be returned. And as many of you are well aware, a lot of the equipment that we're sending out to do exploration of the solar system has increasingly high-resolution sensors, and therefore more data has to be transmitted back. But of course, the most important thing is getting all those cat videos out there to the rest of the solar system. After all, we wouldn't want the Martians to be disappointed that they couldn't get access to the most important content on the terrestrial Internet. Seriously, David has been a huge contributor to this whole concept of interplanetary networking, and the work that he has going on at Goddard Space Flight Center, together with many of the other parts of NASA's laboratories, plus the other space agencies that are participating in, for example, the Artemis mission, which is part of the return to the moon effort. All of those things are the beginnings of networking that will eventually take us to Mars and beyond. And what's important here is that the lunar experiments essentially help us exercise the technologies that we will need for much more distant communication. After all, the moon is only 250,000 miles away. So the latencies are relatively low. We're only talking about a 2.5 second round trip time, whereas the latencies that go all the way to Mars could be as much as 40 minutes round trip. And of course, it gets worse as you get to the outer planets. So the architecture of a network that spans the solar system has to involve protocols that are different from the ones that we use terrestrially, like TCP/IP or quick over UDP. In the interplanetary system, we've developed something called the bundle protocol. And this needs to operate at very high speeds as well as operating at high latencies. And that's why the cat videos are important, because what David is doing essentially is increasing the capacity of optical channels to carry information to and from the planets. So I hope that you'll enjoy David's presentation. He'll give you a sense for what's possible and what our aspirations are as we move into the rest of the 21st century.
Hey, this is Keith Scott. I'm another member of the IPNSIG board, and I'd like to say a couple of words here before Dave gets started. You can read the blurb about what's going to be in Dave's presentation online, but just to expand a little bit on one of the topics that have been brought up, Dave has been involved in the bundle protocol work and in extending the Internet into space since very early days, back when the work was being carried on in something called the Cislunar Internetworking Working Group within CCSDS. And it was Dave's sort of immediate understanding of the potential benefits of network communications, the ability to be able to simplify missions by having a single interface into a network of shared resources rather than sort of one-to-one interfaces with every other mission that you might want to communicate with, that brought a lot of NASA together. And he was able to rally large parts of NASA around the DTN effort, and also of the rest of the space community through the interagency or operations working group. So that work really has been instrumental in bringing DTN forward. And so we really thank Dave for all of that as well. So with that, Dave.
So thank you to Vint and to Keith for the kind and generous introduction. So I'm Dave Israel. I'm from NASA Goddard Space Flight Center, where I'm the architect for our division, working with the Near Space Network. It's also part of my job has been to be the principal investigator for the Laser Communications Relay demonstration and the LunaNet, and you'll hear the details all about that. DTN in general is a very large effort with a lot of people involved. This particular set of experiments and demonstrations that we're talking about also was the success of a lot of people, and two of the lead people involved are also going to be presenting today. Alan Hylton, also from the NASA Goddard Space Flight Center, was the principal investigator for the overall end-to-end DTN experiments with the LCRD, and Daniel Raible from NASA's Glenn Research Center, who is the lead for the High-Rate DTN experiment. The way we're going to do this is all three of us are going to present. We're targeting to keep it within the first hour, because we do want to allow time for questions and interaction. So here we go. Just a top-level summary, but we will be talking about all these items. We first did the DTN over Lasercom links in 2013. I'll have a chart on each of these items coming up, but just the top level, we did DTN over Lasercom links in 2013 for the first time. DTN's been used operationally from the space station since May of 2016. The PACE mission just launched in February 2024, and that's the first science mission that's up there that is now using DTN operationally. So I'll give background on all that. Then we'll get into the specifics of what LCRD and LunaNet are about, and we'll tell you all about what we just completed during the month of June, essentially, and we'll work in how this relates to where we're going within the Near Space Network, NASA's network in general, and then also the LunaNet concept that I've previously presented to this group before. So I think one of the first one of IPNSIG events in 2014, or I know there's one out in California, was fresh after the Lunar Lasercom demonstration happened. And the thing that's important to understand, you see that footnote there, is that this was a Lasercom platform that was on the lighting mission that orbited the moon. And once it was up and running and performing successfully all of the Lasercom demonstrations, then Don Cornwell, who was the principal investigator for that experiment, allowed me to piggyback DTN experiments onto this mission. So we ran data using DTN, using bundle protocol and LTP, and set up this whole thing to make it look like it was a lunar relay. But we ran all of the DTN on the Earth, but it was bundle protocol and LTP going over the optical space links. And so we really demonstrated DTN's capability to take care of outages due to clouds on optical links, and that's what this graph is on the right-hand side is showing. Also critically, to do rate buffering when the data rates from the optical links to and from the ground station are at a higher rate than you have terrestrially, or the links from the relay are at a different data rate between the relay and the user on the surface. We modeled all of that, and then also the networking function of multiplexing and demultiplexing the multiple users. So there's a paper, and I'm sure in the IPNSIG archive, there's a recording of the full presentation on this experiment. So that was over 10 years ago in 2013. Now, just focusing on the near-Earth uses of DTN and demonstrations, then a key one that is operational since 2016, DTN is being used operationally from the International Space Station to send the space station science payload data, but now also other data to and from the space station routinely. They're getting their science data and their data back and forth. And really, one thing I guess I do want to make a plug is I do recommend that perhaps the IPNSIG should schedule up, or there should be a discussion and a presentation from the folks from JSC and the HOSC at Marshall about their experience, because this is certainly the longest running space-based service of DTN that has been used operationally. So when that talk happens, and they can give you all of the details, but the one main thing I wanted to point out in this picture is you see all the DTN nodes, and what you don't see is that right in this space where you just see these lines going in between the ISS and down to the Earth, this is the MCC in Houston, this is the HOSC at Marshall Space Flight Center, is that there's a TDRS relay satellite and the ground station, the White Sands, New Mexico, and all that is inside of this line right here. And TDRS is now part of the Near Space Network. And the significance of this is that this is really the model For those of us that were first dialing into the internet, you'd say in the 90s, when you used your local phone company and your modem to dial into your internet service provider, then that is exactly what the TDRS system is doing now for the DTN traffic to and from the space station. And really the host is the DTN network service provider for the space station, and the data that comes through TDRS just looks like any other data that comes through, and the network provider itself is unaware of anything related to the DTN traffic that's happening. Okay, so just real quick on how PACE is doing their data operationally. This was a big step for us to declare this as an operational requirement and not a demonstration. What that means is that all of the development, all of the testing, all of the operations has to go through a lot more rigor and details in order to be used operationally. A lot of times when something is a demonstration or a technology objective, then some things are just considered that's good enough for a demonstration, but then it doesn't necessarily really bring things out and get it to an operational state. So with PACE using DTN operationally, then we've been through all that. One thing to point out, PACE does have 4 ground stations. It's a low Earth orbiting spacecraft. With those ground stations, it does command telemetry at a low rate over S-band, around 2 megabits per second. And then there's science at hundreds of megabits per second, science link at Ka band. The DTN is only being used on the S-band link at the lower data rate. So it's not being used for science yet, but we are getting all sorts of experience in DTN in the operational scenario. It launched in February, and the DTN performance has gone very well. The project, as a risk mitigation, has on board the ability to send these files down without using bundle protocol, just in case, because it was new, but bundle protocol is doing the job just perfectly. Now, the thing that I wanted to point out, this hypnotic animation going on at the bottom here, what this illustrates that's different with this architecture is that you see that we're doing custody transfer, but when the spacecraft sends its bundles to one of the 4 Near Space Network ground stations, then the custody signaling is generated from that ground station node. However, those custody signals, you see, have to flow back to the Mission Operations Center to then be put onto the uplink and back to the spacecraft. And that's what these red dots are that are going diagonally up there. So this was necessary in order to meet the requirements and the ops constraints that the mission had, that all of the data going up to the spacecraft needed to come from the MOP. So you see that the second hop here between the ground station node and the MOP, which is where the file data is going, that the custody signaling goes directly back and forth. So that was an architecture constraint that we had. Another constraint that we had is that there's 4 ground stations. The MOC has to separately connect to each of the ground stations when the pass occurs. So just hold that thought for a little bit. Okay, now very quickly for LCRD, I don't have time to get into all the details about the mission, but for tonight, the thing to know is that there's an STP-SAT-6 spacecraft at geo orbit. It has 2 optical terminals on board. Each of those optical terminals are capable of bidirectional communications. The maximum data rate is 1.2 gigabits per second. And there is also an RF ground station. So there's a Ka band path also to send data. And then there's a switch on board the payload that allows the data from any of these terminals to be switched and forwarded over to one of the other terminals. So for example, you can come up through one of the optical links and be switched the data to do an optical to optical relay, or you can do an optical to RF relay or an RF to optical relay. There's also 2 optical ground stations. OGS-1 is located in Table Mountain, California, and OGS-2 is in Haleakala, Hawaii, and the RF ground station is in White Sands, New Mexico. So LunaT then launched in November of 2023. LCRD's been up since December of 2021. LunaT provided our first orbital user of LCRD to demonstrate that we could do that optical to optical relay and optical to RF relays through LCRD from orbit. It was a 6-month mission. Sadly, it was jettisoned at the end of June, but you'll see that we certainly got all that we were hoping for and then some during the time that we had it. The thing to note, though, that the maximum return rate that we could send data from T, the ISS back, is this 1.244 gigabits per second. Really, it was on a 1 gig Ethernet connection, so that was the maximum rate. And in the forward direction, so from the Earth through the relay to ISS, we could run that at 155 megabits per second. Okay, so here's where we get to the LCRD experiments and goals and the ground rules. The way this worked is we've been planning from the beginning to do DTN experiments, even from the beginning of the LCRD project. This has always been a goal and plan. And so what happened is I defined these goals, working with Alan and Dan and others with the experiment goals, and laid out the ground rules, and you'll see in the next picture the architecture. But then it was really Alan and Dan and a team of many people that then pulled it all together. So after these next couple slides, I'll hand it over so that you all can see it. Now, I can say that I don't know how many people are out there on the line, but right now the only two creatures that are here live listening to me talk are Ernie the cat, who's here having a Teams meeting with Vin. And we've all learned that sharing pet pictures and videos is a good way to get people involved, right? So here were the goals. So we wanted to demonstrate a bundle protocol at the maximum rate through all of those various paths that you saw. So that includes optical to RF, each of the 3 different ground locations, and each of the modems, etc. We wanted to use bundle protocol, both the V6 and V7. The space station now uses V6. But we wanted to also, and I should have mentioned that the PACE is also using V6, but we wanted to put V7 into action. Wanted to demonstrate BPSec for end-to-end security through an intermediate provider, and you'll see that network in next chart. Here's the things related to the optical and the optical relay. We wanted to show that bundle protocol, LTP, whatever protocol resources we had available to us would allow us to demonstrate that you could do complete data delivery when there is dropouts on the optical link because of clouds, when there's outages because of atmospheric effects, and even when you have a handover from one ground station to another ground station, or that the space station could start sending a file during one contact, it runs out of time, comes back around and sends it down the next one. So we want to accommodate all that. And then also this demonstration of doing streaming video using the bundle protocol. A little bit of a spoiler, I'm thrilled to say that we were able to get all these things done. You'll hear the details. So the ground rules, though, that I laid out is, so I put together this network provider architecture, which I'll discuss, and then also no cheating was allowed. So all end-to-end data delivery had to be done using a bundle protocol. This was a relatively low latency environment, about 4 seconds latency on the links because of the combination of processing, and bidirectionally, there's 1 second interleavers on the links, but you could still make it work with IP to do the things that we were doing, but so there's no cheating, have to use bundle protocol. And then the last one is that the end users, and in this case, I mean, whoever the terrestrial node is on the ground, that our destination and the ISS needed to be able to just flow their data without having to keep track of which of the ground stations the trunk line was going to. So here's the network picture. Here's the ISS, has its DTN gateway. And the thing is that the ISS is always talking to the LCRD spacecraft, but the ISS shouldn't have to know whether or not the LCRD is going to relay the data to ground station 1, ground station 2, or the RF ground station, we call it the piglet here. And then that's why there's this LCRD edge node, so that in the forward link direction, things sending data to the ISS, also from a routing point of view, shouldn't have to care which of the ground stations that data was going to flow to. You just get the data to the LCRD edge node. The LCRD edge node is responsible for getting the data through that part of the network. Similarly, then there's the near space network edge node, which, if I say, for example, that we had the TDRS link as also a possibility to get to the space station, then you could see where maybe there'd be a TDRS edge node that would also be connected to the NSN edge node. And then it's at this NSN edge node that is able to control whether the data goes to the TDRS connection or to the LCRD connection, for example. And then all of the terrestrial users are then seen as near space network users, and they are connected through this NSN edge node. So I think I gave a talk at some point to this group about the LunaNet architecture. and mentioned the near space network and just this idea that there's going to be multiple providers, but we want to kind of separate out as much as we can the intricacies and the handovers and the peering connections between providers as possible from the end users. And that's where this edge node architecture comes in. So that's why I insisted that this was part of it. So I tried to cover a lot in a quick period of time, but now it's time for me to hand off to Alan.
So yeah, I'm Alan, but you guys can call me Alan. Then I'll just start off here. I'm actually not going to go too deeply into the NSN, but I want to focus on here is that the NSN is growing. The scale is growing. And this would both be in the number of users, but also the amount of data that's needed. And so somehow to support all these needs and grow into the future, we need to take on new capabilities. And of course, the optical work that Dave mentioned, as well as the networking, are both essential ingredients. LCRD, also as mentioned, brings on some interesting new capabilities and new challenges. Of course, there's some of the optical challenges that Dave mentioned that we're going to want to be able to more or less low-pass filter somehow. And of course, DTN is the answer. Rather than talking too much about LCRD, what I really wanted to say here is that this has really created a bridge between the ISS and the ground network, which is the platform upon which we did most of our tests. It gets a little bit more interesting than that, but I do want to say LCRD has provided a fantastic window for the NSN users into the future here. This picture is a pretty good summary of what things look like. We have on the space station that LunaNet are used to. It's jettisoned, as mentioned. Won't dwell on that too much. But the LCRD gave us this bridge between our 3 ground stations and the space station. And really here, we wanted to use LCRD and its corresponding ground infrastructure as a service provider for the ISS, taking us kind of a step forward for DTN and a step closer to that there LunaNet. Maybe just an extra word on that by service provider. I really do mean that I want to have DTN giving like network services in space, a space-based network service provider. And the ability to do this is going to be absolutely important for LunaNet. LunaNet will give us a non-trivial network with a non-trivial number of such service providers, the NSN being only one of them. And somehow we're going to have the underlying protocols that can give rise to a network solution to take all this complexity and make it make sense. But of course, it isn't really just about the protocols. There's also the architecture, management, and all these other aspects to make the protocols do what we want. Of course, DTN helps us overcome the interesting realities of communications in space. What I wish to show here is that it gives us something scalable and that we can, in fact, take DTN and thanks to our operators, our implementers, and perhaps even the architects, we can, in fact, make this work out. The true vision for the solar system internet is very broad, and Vint brought this up in his recording. If we're thinking about Earth to Mars, we're thinking about minutes in one way. And so this will preclude any kind of reactive communications feedback. However, really any kind of network should be pretty heterogeneous. We see this on the ground with the myriad of devices that connect to the internet. Here, we have heterogeneity in other ways. If we are the moon or closer, also as been mentioned, we can take advantage of this. We can have single-digit seconds of round-trip time, not just minutes of one way. So we can use this to our advantage and perhaps use discovery. I wish to bring this up simply to say that we did with LCRD and space station. I'll get into this a little bit more in the next slides, but before we do that, to kind of make things a little bit nicer, we had contact plans that were essentially always on, but we did probe in band to see if the lights were active. And if they were, then we could send and receive or not. However, there was other forms of complexity We have multiple ground stations, as Dave mentioned, and we also have multiple capabilities. When we really think about service provision, kind of like your cell phone, you don't think about it unless there's something wrong. You never really want to know who it's talking to. But we wish to contain the LCRD complexity somehow within its own little network. But we also want to control for the different capabilities of the different ground stations. So maybe that's a little bit of an oversimplification, but the idea is that the RF was the slowest. The ground station and the Haleakala gave us low hundreds of megabits per second terrestrial capability to continental United States. And then from Table Mountain, we were able to hit the full 1 gigabit rate, but we were only able to hit the full 1 gigabit rate if we used DTN at Table Mountain, because once again, the terrestrial link was in fact the bottleneck here at 300-ish megabits per second. So to actually make Illumity, LCRD, and indeed the DTN network operate at its full capacity was necessary to run DTN on the ground station to overcome the asymmetries. So all of this stuff going on, we want to try to figure out how could we make it even more complicated? And the answer was, well, what if we had an optical link to an aircraft? And so that's exactly what we did. Here we see on the right-hand side an aircraft with a laser terminal mounted on the bottom, and then on the left, there's the corresponding ground station. So all in all, what this means is that we could have this aircraft flying around Cleveland, Ohio, with its optical link to the hangar at NASA Glenn, Cleveland, somehow connecting all the way up to space station. What I just said actually has quite a few moving pieces in between. And so now what I'll do is I'll start talking about how we actually connected this up. So this is actually a good place to dwell for a minute. If we had an omniscient view of our network, it would look something like this. On the left, we have the ISS, where we had a couple of nodes. Of course, there are many other nodes, but this is what I had to work with for this experiment. And then we have this LCRD system. So I'm not really going to talk about the LCRD satellite here so much other than to say that there's 3 links, the 2 reds up at the top, and then the purple one for the piglet, which is the RF on the bottom. The LCRD network had 3 DTN nodes plus a 4th DTN node, which was the edge of our LCRD network, so all contained in that box. I'll actually pause right there to say that this gateway node on the ISS, node number 1, part of Dave's ground rules were that one would know it could talk to this LCRD ground system, but it wouldn't really need or want or even be able to know the particulars. Is it talking to node 10, talking to node 11, talking to node 12? It should simply know whether or not it can talk. So I'll go into that a little bit further in a second. The LCRD network was all contained at White Sands, with the exception of the OGS-1 DTN node, which was physically installed at Table Mountain. And the edge node for LCRD was connected to a cloud node. And this cloud node was run out of just AWS GovCloud. We were able to make that work, which was really, of course, a feat of rules and agreements and so forth. And that cloud node was really the gateway between everything on the space and space support side and our ground side, which would either be the HOSC, the On-Spot Operations Service Center at Marshall, or the DEN, the DTN Engineering Network up at Glenn. And just looking at this, we can see that if we were to make a contact plan, if we knew what station was being talked to at what time and everything, we could definitely make just a regular old CGR routing table that makes this work. But if we did that, it wouldn't be particularly meaningful, not just in the sense that it would violate the ground rules, but in the sense that it isn't really scalable and doesn't represent a movement forward in terms of DTN architectures. It doesn't really represent what I was talking about earlier in terms of the service provider. We don't really want node 2 to know every last detail about everything else. So now I'll tell you a little bit about what we did, starting with the HOSC, because that's perhaps the most fun side. So I kept that diagram up above just for reference. And on the bottom, I have what the routing table for the HOSC node 31 highlighted in red would look like. This is just a way of managing routing table size and complexity. Really, node 31 in our tests only talk to node 2. And what that means is it only needs to know how to get to 2 in the most basic way possible. All of its bundled traffic is going to have to go through node 30, and node 30 can somehow make it to 2. So even though it is a bit of a lie, that's really what the routing table looks like. And this definitely suffices. Now, this isn't brand new in terms of capability. It does kind of show the practice that we took, and we did this sort of thing quite liberally. But what I want to emphasize here is that the different nodes had different routing tables and different routing information. So the typical approach to the CGR, globally distributed, globally consistent, it was not followed. But the type of future work that we would really benefit from here is that what node 31 really needs is a default bundle route. Instead of saying, oh, here's the path to 2, it should just say, if I don't know any better, I should just somehow forward bundle traffic to node 30. And hopefully 30 configure. This is something I think would benefit from some further research, particularly from this group. But yeah, this is kind of the soft introduction. Next slide, please. All right, now this is where things get a little bit more interesting. What did the network look like from the perspective of my ISS gateway node? Now, the ISS gateway node needed to be able to send bundles to and from the cloud node. So that's node 20 in the middle there. The aircraft, node 43, and my Trek node on the HOSC, node 31. It also needed to be able to talk to node 2, its neighbor on the ISS. It did not need to talk to the ground stations or the LCRD edge node in the sense that it didn't need bundles that wasn't really the destination for the bundle. So it's always a pass-through. And this is a little bit of a simplification of what went on, but this is the important part. But wait, there's more, right? This node 14 sort of sprouted up out of nowhere. The idea here was that node 1 would either forward traffic that was destined for node 2 to node 2, or the next bundle hop was always node 14, which represented the entire LCRD network. But there was no node 14. There's no physical node that corresponded to it. So 14 could always be the next hop, but it was never a destination. So what that meant in our case was that we could send, if the link was up, to node 14, and either nodes 10, 11, or 12 would receive it. And hence, we were able to satisfy the rule. Node 1 has no idea really what's happening to the bundles once they leave the space station. Where they're going doesn't really matter. It's going to get where it needs to go. The way that we made this work, so if you thought I was going to bring up future work again, you'd be right. We made this work with a little bit of an LTP trick, which is that we gave the LTP link. By the way, this was the only place LTP was used between 1 and the LCRD network. Everything else is just TCP. But 1 and the ground network here, the LTP engine ID between 1 and 10, 1 and 11, and 1 and 12 was the same. And from the ISS perspective, the IP address was unchanged because even though the machines 10, 11, and 12 had their own IPs, there was natting that happened on the ground, depending on which ground station was active at the time. And this worked great, but it was not a enterprise solution to, say, DTN multicast, anycast, broadcast. We were able to make it work in the sense with, again, the LTP trickery that I brought up. However, we would have benefited from more robust approaches. Nevertheless, it worked great. And so we were able to send traffic from 1 to 14 and get the bundles where they needed to go. And we were able to, therefore, also support handover. We forced handovers between ground stations. And we also forced clouds between the laser and our ground stations. And we were able to accommodate all of this automatically through DTN without node 1 having any additional burden beyond knowing it needs to talk to 14 to get to where it needs to go. For fun, I thought I would also mention the architecture from the cloud's perspective. The cloud knows that if it's going to send traffic to the aircraft, number 43 in the upper right there, it'll have to send it to 40. It knows if it's going to send traffic to 31, it'll have to go through 30. But if it's going to send traffic to the ISS, it also only knows about node 14. It doesn't have to know about the LCRD edge node. Once again, we can have everything in the LCRD bubble there represented by this phantom node number. And just node 14 somehow connects to either 1 or 2. So this approach works quite well. And of course, here we didn't have to do anything funny because there's only one link from 20 to 14. Although, what I will emphasize here is that while node 1 doesn't get to know if it's going to send bundles to 10, 11, or 12, of course, within the LCRD network, we know which ground station is active at which time. And so internally to LCRD, we know where to either stage bundles or not. Again, this allows us to contain the complexity of whatever's going on in LCRD. And this is why, or this is how I should say, we were able to have DTN give us an architecture that resembles some kind of service provider. I'm going to give a high-level overview of the tests. I think that's more important than really going into the nitty-gritty. So as far as BP goes, we did BPv6. The only BPv6 tests that we did were from the Trek note, and we did that with custody. We actually ran out of time to try it without custody, but we're pretty confident that if it worked with custody, it would work without. And then actually, I'll just mention really quickly that the HOSC operators and everybody who helped us with the Trek showed enormous patience as we tried to make all that work. So I'm very grateful for their involvement. And then BPv7, we did with and without BPsec. Of course, we knew it was safe to do BPv7 in space, thanks to our European friends who were able to blaze that trail for us. And then we tried to take it a step further by using the HDTN BPsec implementation in all possible configurations, and that worked quite nicely. We sent files. We sent small files, so we collected the cat pictures and cat videos. We also had large files, and this was pseudo-random files to say like 5 gigabytes in size. And we sent just combinations, basically just a directory at a time of small files or large files just to see how it goes. We also did video streaming. And this video streaming, we did it to the ISS. So we have the HDTN gateway, that was node number 1. It received videos. Nobody got to watch them, which is too bad, but it worked. And then we were able to stream video from the ISS to the ground. This was a basic idea of all the tests. Next, please. All right. The results, I'm not going to read all of these to you, but here I will emphasize the pieces that I think are the most important. We definitely made the optical link make the most sense with DTN because we were able to overcome everything from handovers to quick outages and so forth. And we were able to show that DTN is not the bottleneck because we were able to essentially max it out, I think, at 981 megabits per second. I also believe, I'm pretty confident, that the bundle size was around 100K per bundle, and the LTP segment size was small enough to fit in the packet without fragmentation. It's around 1,400 bytes or so, somewhere in there. We showed that the architecture I mentioned made sense. We were able to do a lot of interesting things, but what I can point out here is we also used DTN on top of all the things I mentioned to achieve kind of a cultural break from the past. What I mean by that is it used to be that everything the US sent or received on station went through the MCC. That was not the case here. We sent files to the ISS from the ground, and we sent files to the ISS from our aircraft. We were able to send files from the ISS to the ground and to our aircraft without the MCC. We even were able to stream video to and between the ISS and the aircraft in both directions, once again without the MCC, showing that we were actually able to really provide this new type of communications going beyond bundles, kind of show new philosophy of data transmission and networking in space. All right, so a couple observations. We were able to use DTN to contain that complexity of whatever's happening in LCRD. Nobody outside of the LCRD project was burdened by all the choices and so forth that were being made. And in that same line of reasoning, we show that DTN was, in fact, able to join those networks and those bubbles that I had shown in the architecture section, which actually represents going across project and programmatic and NASA-centered boundaries. We had so many teams of teams involved, all running their own segments, and we were able to patch it together and make it work. And this, I believe, not only showed that we were able to bring the architecture, the number of assets and everything together into a network, it also showed that we can make an even stronger case for Lasercom than before. And because we were able to install DTN at the ground station I mentioned, if we use that ground station, we could actually use DTN to improve the amount of data return per pass by using DTN to overcome the rate asymmetries to and from that ground station. So what I'm hoping to do from here, at least within NASA, is, of course, make the most out of this operational capability. We had, I believe, 21 operators total for this experiment alone. That's a lot of people running and suffering DTN, people actually making DTN work live while a pass is happening, debugging things, enjoying the triumphs when they happen. As Dave mentioned, we were able to check every one of our boxes, which feels pretty good. We also hope that from here, we can strengthen our case for DTN infusion, both into the NASA networks and the missions, and use what we learned here to inform ourselves on how we wish to do that. And the capability that we showed with the aircraft was amazing. So I'm hoping that we can also use DTN to strengthen our relationship with the aero side. I imagine Dan will talk about this, but let me just mention here that also super grateful for the flight crew at NASA Glenn, who has been dedicating many hours to pushing a lot of the DTN capabilities forward, and also giving us a free space optical, at least I imagine there's no tether link, to this aircraft to make a lot of technical improvements and train people on how to actually use DTN once the bundles aren't traveling from one side of a bench to the other, but actually doing things live. And then finally, I did want to mention a couple things I mentioned before, a couple things I didn't. I'll actually read these out of order. The multicast, broadcast, anycast, looking forward as we start to have multiple ground stations, especially if they're all owned by the same group and managed by the same group. Finding ways to collapse them would be fantastic for containing whatever the complexity is for anything like that. Hopefully the next versions of LTP could also learn from what we did to figure out how can we not only scale things better, but when we're using LTP with a short enough round trip time, are there ways to have adaptive rates or adaptive configurations? I think the answer to that is in fact already a yes. I'm working with the people who actually ran all the experiments to capture their lessons learned, but I really want to second Dave's idea of having an IPNSIG talk given by people who are actually doing this. They will be able to provide a very unique and valuable and essential viewpoint into DTN that it needs to make sure it grows in the direction that's needed. And BPv7 with custody, man, I wish we had it. We've actually done previous tests where we showed that bundle protocol with LTP with custody will give us 100% of our data back over that very same plain optical link, whereas BP with LTP, everything read without custody, does not. So I lament the decision to not have BPv7 with custody. I hope that at some point that gets addressed, hopefully in BP V8 or 9. Now, right before I turn things over to Dan, I wanted to say that this test campaign attracted a lot of positive attention. This is Doug Wheelock, previous ISS commander, who happened to be in Cleveland when all of this was going down. and took a personal interest and time out of his day to not only record videos for it, which were part of the streaming experiments, but to help proselytize what it is that we're doing. And so I'd like to thank him as well for helping us move this forward and help us, when we're talking about DTN, talk to people outside of the choir, as it were. But you're all lucky I'm out of material, so I'll turn it over to Dan.
Thank you, Alan. So it's been very exciting to be able to support LCRD and Illumity and DTN. And I am very grateful for the opportunity to humbly represent a team greater than myself in all this. So to set up just the why of the media streaming, talking to people like Wheels and the Astronaut Corps, there's a strong interest in astronaut health monitoring for crew activities from a flight surgeon perspective back at Houston. So having things like 4K video during important events like EDL would be really nice from that perspective. But then stepping outside of NASA altogether, public affairs, PAO type events in the future, so that we can get the public better in touch with their space program and share some of that imagery live or at least in a delayed fashion, or some of the desirements that we've heard for why we should consider what can DTN do for video streaming. And then lastly, thinking of it, and especially coming from the Johnson folks, about the importance of the forward link. We're asking a lot more of our astronauts than we were with Apollo. Going out for an Artemis mission in the future is going to be much longer duration. And so connecting them to the creature comforts of home and being able to do things like video conference with their families also plays into astronaut health, and particularly mental health and that in the future. So that's kind of some of the why in that. I'll show you a bit more about the how. There is a CCSDS Motion Imagery and Applications Group, which we were directed to from Joshua Deaton, which had a red book on how to implement a bundle protocol-based real-time transport protocol, RTP. So RTP over BP. And last summertime, we were fortunate to have a SCAN intern joining us, Kyle Vernier, which looked at that draft standard and put together a prototype, which you can see the send on the top and the receive on the bottom. Essentially, what it does is it can ingress some RTP packets, and those can be either from a file stream or a live camera, and it runs through a circularized buffer where we can concatenate one or several of those RTP packets into a bundle queue, and then onto the rest of the DTN service processes. At the receive side, then you're basically doing the inverse of that. So we receive a bundle and then run it into a circular buffer where we deconcatenate each of those RTP packets to then do one of two things. One would be, generally speaking, someone is viewing the stream live, and maybe that's several people as well in a multi-destination format. And then two, you're saving that stream to a file for archival later utilization. So from a use case perspective, if you're in the cislunar environment, perhaps you're having a synchronous conversation then with someone because you're only a second, 0.2, or a little bit longer time delay. And so maybe some disruptions are happening, you're dropping some frames, but you still want to have a somewhat synchronous conversation, but you would like to have the full thing in archival for later utilization as well. So that would be on the back end of the system. So that prototype was put together, and we started looking at, well, what kind of metrics should we use to determine how well DTN and this implementation of RTP over bundle protocol is doing? That's what you see in the lower right-hand corner. There's several very heritage legacy specs that many of you might be familiar with, whether it be the video side or the audio side, which would be peak signal to noise ratio, PSNR. So we used that on both of those. There's, on the video side, another index called Structural Similarity Index. So that's kind of looking at the source and the destination. You compare them both and looking for the differences between the two. And then lastly, we have something called VMAF. This is a very interesting one. This is a trained model put together by Netflix, known as Video Multi-Method Assessment Fusion. That is basically a model that was trained on the user experience. And similarly, it's kind of between 0 and 100, where anything around 93 to 94 matching between source and destination would be imperceptible to a human as far as which is the source and which is the destination in terms of any degradation effects of that. So that's kind of some of the post-processing that we were using. The last thing I wanted to mention about video is the quality of the video and also the stress on the communication system is very program dependent. So complex content, like the content that you see here on the screen, this just very gorgeous bubbles forming in microgravity, are very stress-induced onto the encoders, and especially so with software encoders. So we used a lot of that content to evaluate how things were going in the laboratory and all the way up to the full house 4K 60 frames per second. Now, I think the DEN has been mentioned a couple times here, and I only put this chart in here for a minute to just say the DEN, the DTN engineering network, in history has been more of what you see in the upper left-hand corner, kind of a collaborative network for agency and academia to work together on DTN development. It still exists that way, but it has evolved to having a lot more going on, which you see in this chart, that includes both hardware testing, so hardware in the loop. So when we started doing this video implementation, we've used things like Raspberry Pis and NVIDIA Jetson Orins, which you see in the lower left-hand corner. That is all part of the DEN as well. We have also physically connected the DEN to external networks, as Alan pointed out, going through Amazon GovCloud. That's our portal out to LCRD. It's also a portal over to the flight research, so the hangar over at Glenn Research Center. Also connects to the DEN. And the last thing I'll just point out is in the middle, what we have is a Netropy network emulator. This is basically our wrench that we can throw into gears of things. We can artificially induce delay and out of order bundle delivery and things of that nature, which we'll invoke here in a chart or two. I just want to show that so that when I say DEN, you understand this is the evolved DEN that we're using now. So step one, when we had our prototype, was to evaluate it in a range of different video capabilities. We got Rodney Grubbs and the rest of the NASA television team with their cameras in the laboratory, hooking up to DTN nodes, running HDTN, and tried all the different video settings all the way up to 2160 at 60 frames per second, 264 and 265, and different bit rates, just making sure that everything was functional and we were getting good PSNR values, good SSIM values. And what we learned from that is we were always at an excellent video quality across the board, sending 4K video, even full house 4K video across DTN. Now we start to throw the hammer at things. So we invoke the Netropy, and we start to invoke things like reordering and duplication on our bundle delivery system. And here's the big lesson. So when we look back at those concatenators, at the source and the destination, when we would take one RTP packet and place it in one bundle, we would see very poor performance, on par with not having DTN in the loop at all. So the first kind of four outcomes at the top in red are no DTN, just run RTP right over with the disruptions induced by Netropy. Then we add HDTN in the mix with only one RTP packet per bundle, and we see about the same performance. We can see that objectively here, but even on the video monitor, we would see very clear blocking and degradation of those signals. When we start to increase the amount of RTP packets per bundle on the concatenators, so we increase to 5 RTP packets, and then the bottom 4 test cases, the same Netropy settings, but now 20 RTP packets per bundle, enormous increase in performance. Now we're getting up to the 92-93% of where human imperceptibility of any of the deleterious effects. Things are looking very good. They're not distracting for trying to do a live video conference with someone. And so that was a big learning tool in getting ready now to do the LCRD experiments. But again, this is in a laboratory, a controlled environment. To show you what this actually looks like, when we did start the flight testing, this is what a live video from a camera in the hangar transmitted over to the aircraft in flight looks like, with only 5 RTP packets per bundle on a not so great day, a lot of thermal blooming going on and a laser link kind of fading in and out. That's me in the center of the screen flapping my arms. Of course, what you're seeing is a highly blocked up version of myself because what you're seeing are some of those effects that the Netropy was doing artificially back in the lab, but now Mother Nature taking care of that for us. So that's what one would expect to see with those low numbers of, let's say, 0.5 or 0.6 SSIM or VMAP. I didn't want to really rehash this too much, but just to say, Alan had the nice diagram of the network topology, looking at it more physically here, connecting the DEN to that existing topology, and then an aircraft off one leg of the DEN to the right-hand side. We have an aeronautical laser communications link to the right, working at 1 gigabit per second, down to our DTN engineering network, then over to the LCRD network through that AWS node. So that's kind of the leg that we added. And just as at the tip of the hat of the giants of whom we stand on their shoulders, we named the endpoint HDTN node on the aircraft as SURF, and the other endpoint on the ISS as Hook. And so the whole purpose of the experiment was to get Hook talking to SURF and do video streaming bidirectionally from that. You'll start to see here what things should look like when it runs properly. Increasing then to about 20 to 25 RTP packets per bundle and repeating these experiments. We did a couple things. We had some great videos provided where we would stream the videos both directions. We had ISS crew videos, and we had Astrid the dog bringing the creature comforts to the astronauts, so to speak. They're visually very clear when you crank up beyond that threshold of about 20 to 25 RTP packets per bundle. So that seemed to be the inflection point for us. As well, on board the aircraft, we did live streaming from a camera, also at 4K, and saw similar results. Bringing that back down to 5 RTP packets, we would see similar effects. And I know some of these days, especially earlier on when we were doing this, we had a lot of thermal activity at the West Coast and Hawaii ground terminals too. A lot of weather out there. So that was a good lesson learned for us through all of this. And I'll mention, we did do this with BPSec enabled, both in terms of authentication and encryption across the links. In concert with the flight testing, now just to look at the robustness, we have been running the 4K live stream app on DTN across our LunaNet network in the laboratory for 3 months uninterrupted. We have a camera on there going through a multi-node, multi-hop network, just showing that it doesn't choke after 24 or 48 hours or 3 months of continuous operation. We get some of the performance testing from the LCRD tests, and then we get the longevity testing from our LunaNet infrastructure here in the laboratory. And that's in hardware, I should say, again, as part of the DEN. So going forward, we've actually continued flight testing beyond the disassociation of Illumity from the ISS. We've generated tons of data, even with Illumity. So we're continuing to do some post-analysis, calculating up the SSIMs and the VMAF. And since then, we've upgraded our streaming application to include the audio with that, and have been developing a DTN video conferencing application, which kind of encapsulates this core functionality into a way to hold a two-way synchronous conversation with someone. We'd like to do more investigation into LTP tuning optimization to try to optimize video stream across the DTN. We've also gone on to send command and control to the cameras across DTN. So now we can change resolution and have proven all that out in frame rates and zoom. What we'd like to start now doing is closing a little control loop, or maybe by doing some link detection on the performance of the communications link, we could ask a little more or a little less of the camera to optimize the quality of the stream in a real-time fashion. That's really exciting to us. So that's something that we're getting into right now with our flight testing. There's been a lot of asking of, okay, well, what about multi-source? Makes a lot of sense. And multi-destination also makes a lot of sense, and both. With LCRD being a great asset out there for a period of time, we'd like to demonstrate some of those capabilities as well going future, and just continue field testing these networks. So we'll be continuing with this. But that said, we've generated so much data now. We also kind of have to take a bit of a pause and do some writing and publishing to get all this out to you and understand how better to formulate new experiments going forward. So quite an exciting time. And these products are part of the version 1.3 release of HDTN, which came out just prior to this flight testing.
Okay, so it's back to me real quick, and then I want to field some questions. So as you can see, it was really highly successful. And again, huge thanks to all the team. The list of the people that helped make it possible is incredibly long. We were racing against the clock because LunaNet was going to be jettisoned off the space station. Sometimes the weather cooperated and sometimes it didn't. And just so many factors. The fact that we pulled off everything that we did was just really a sign of a great team. So just a couple of notes from my point of view. This note about mindsets and operational cultures need to evolve for users to appreciate and achieve full benefits from DTN. There's different things, right? So one thing is, even when you have DTN, one of the things I notice is that people still think of their source and destination and a line between the source and destination. And even if it's got multiple stops in between, they view it as just that, getting people to realize hey, with DTN, you don't have to wait until the full end-to-end path is up to start sending data. If you're using DTN, you can just start sending your data in the direction of where you want it to go and let the network worry about when each of the steps along the path are there. So that's an example of that. There's also the part that I showed in the beginning that's still a very real constraint that we need to work on is this idea that all data needs to be routed back to some control center first before it can get put on the uplink or the forward link to close protocol loops. That works for PACE. We got around that. And with our demonstration where the node on the ground could just talk directly back to the node in space. And that's really the way it needs to work. We don't want to have a situation where two users on the moon want to talk to each other through a relay and they send the data to the relay, but the relay has to go all the way back to the Earth, go through Houston, turn around, go back to the relay, and then get forwarded to that second user, right? I want to be able to close protocol loops at each stop along the way, right? So the next part is really more DTN-based applications are needed. This is really something that I'm taking advantage of having this large audience out there, and I want to encourage people to be working on applications that are looking to use DTN and are assuming a DTN network underneath, and they transmit and receive bundles to make it happen. That picture on the right is a picture I commissioned for the first LunaNet study and presentation. One of the things that I want this audience to view the picture is this idea that, say, there is something like a tablet or really maybe a heads-up display or something for astronauts on the lunar surface, and it's got these little display windows, but these little display windows are being fed different data that depends on what they're doing and the applications. And some of those applications, maybe they're doing real-time data back and forth to the lander, but other things might be store and forward data to and from the Earth and other places. And there are all these separate applications. Some of them are real-time based. Some of them can live in the store and forward world. And we just need to have this view of the different data flows and having the applications for them and having it all able to be integrated together the same way that we do now with IP-based applications on our phones and various devices. And I would say maybe to help incentivize people to be working on applications, I'm the principal investigator for LCRD, so throwing it out there that LCRD is going to continue to be up and running and performing experiments. The space station node is gone, but we still have the 2 ground stations and the RF ground station and the LCRD payload in between. And we have shown we can connect out to the den. And I have requested for us to find ways to make sure that we can, under the right circumstances, control external to NASA centers to be able to expand the network and do the demonstrations. And this is something that I know the IPNSIG community is a community that we can work with to be proposing other experiments and things to demonstrate. We have the DTN nodes and some things in the cloud and things that are shown. I would like to see DTN-based applications where it doesn't require us to change which bundle protocol software implementation we're running in order to load up a DTN-based application, for example. So I'm throwing these challenges out there now because I know the audience that's out in the crowd. So anyway, finally, let's just keep learning and growing from the experience. We could be sitting around for another 20 years just talking about the ideal network and how we're going to do it, but the best way to go And you can see it from the history of how the internet evolved is let's get things out there, start using them as operationally as possible, learn from it because it's going to be different than when we talked about it theoretically. And we'll learn from it and grow from there. And I think we've taken some big steps here and have the facility to be able to really build upon it. So again, thanks for everybody. Thanks to Alan and Dan for their leadership of the various teams and the activities. And again, all the folks across JSC and Marshall and the different centers and ops teams. So I guess I'll talk to Dan and Alan for any last conclusion words, and then we'll take some questions.
Sure. Thank you, Dave. We'll just echo that we wish to test as we fly and fly as we test. And thanks to the people involved, we were able to demonstrate margin. Really, I found this experiment campaign to be one of the most unifying experiences at NASA, to bring together people at Marshall, Goddard, Glenn, and those at Johnson who moved mountains to make all this happen. So thank you. So let's keep the momentum alive.
I'd like to particularly thank the operators that we had the pleasure of working with on all this. You work in the lab for so many years and trying to think about all the things that could go wrong, and then start to proactively think about the solutions for the things that could go wrong. And then you've got tools like the Netropy to break things, but getting out there in the wonderful chaos that Mother Nature builds for us, it's just drinking from a fire hydrant, and in a good way, and just getting all the feedback from the operators that this doesn't work as smoothly as we'd like, or if you only had this, it would really make my day-to-day easier. And we just have a laundry list of great feedback, which creates tomorrow's work for us. It's just such a valuable experience to have that and to see things in operation out there. And I'm looking forward to future field testing with you all, and to try to incorporate all the new killer apps in a DTN, and then break them, and then fix them, and then deploy them and get them in the hands of the customer so that we can be useful as possible. So thank you, and looking forward to the future.
Okay, so I guess, Keith, it's up to you to figure out which questions you want to pass on to us, and we'll try and cover as much as we can.
Okay, I'm going to run through the stuff that was in the Q&A section first, I think. And then there's a bunch of stuff that I've sort of been taking some notes out of the chat. Question from Marshall Eubanks about PNT. With the development of LunaNet and other space PNT networks, integration of communications and timing ranging network capabilities is becoming increasingly important. Is there work being done about time transfer within these high bitrate DTN space network experiments?
I can take that one. The answer is yes. And it turns out to also be a very successful collaboration across centers, in particular between Goddard and Glenn. We have been actually publishing on the theory of a DTN time synchronization protocol, and we have begun realizing it in software, and are actually not only conducting tests within the LCRD ground network, but we're hoping to run time sync tests over LCRD itself soon, whatever that may be.
An anonymous question, what advice would you give someone who's just starting out in network engineering, and what should they learn to be able to contribute to this work? And for any of you take that on, Jorge Amodio posted back in IPNSIG and the PWG working group. Let me put in a quick plug for the projects working group in IPNSIG there, and then throw it over to you, Dave. There is a working group in IPNSIG. If you go through the IPNSIG.org's homepage, there's a whole projects working group. Samuel Grasick, I think, is on this call. They deal with exactly those kinds of questions, and the IPNSIG can get you started with a library of stuff for general DTN, not the Lasercom specific. Okay, Dave?
I wasn't going to say anything specific, but I will say I was very excited about this forum and the work that IPNSIG does to kind of inspire people to get interested in this problem and to be pursuing it. So I'm not directly one of the network developers themselves, so I don't know if Alan or Dan or others have anything more specific than that to say.
I think just first answering some fundamental questions like what type of development would you like to do? The world is your oyster right now. So if you want to go more in the route, if I'm speaking to an undergrad, for example, and you want to go more in the route of an actual DTN implementation developer than focusing on one of the middle level languages like in C++ and that, and pursuing those kinds of routes would be the way to go. But now there's a huge need for applications, and talking to a DTN implementation through an API with a higher level language from a management perspective or something would be up in Python and beyond. There's going to be a lot of work in that in the future. So it depends on what direction you want to go, but definitely the working groups and professional forums are a good resource to start with, and getting your hands dirty with a DTN. We put out a few, but we need to put out a lot more tutorials on YouTube on, at least for our implementation, how to get it up and running and how to get HDTN going on a Raspberry Pi, for example. Go get a Raspberry Pi. I think they grow on trees, so you just pluck one off and go on GitHub and download the code and start working with it in that way. We're going to release some more of that tutorial content in the future as well. And if you have difficulty doing that, then contact us, because that means we're not doing our job the right way. DTN is a mature enough product that it should be easy to get up and operational, and that's on us to ensure. So happy to help with any technical guidance in the future with that, with anyone that wants to get their hands dirty in DTN.
And real quick for the students out there, every summer we have internships working DTN at the NASA centers. So look for those. Also, real quick, any questions? My email, I've noticed wasn't in there. It's just dave.israel@nasa.gov. I can forward to Dan and Alan also if people want to continue with questions and conversations.
So IPNSIG Academy, you can view the other recorded IPNSIG Academy keynotes at ipnsig.org/events. And you can email the secretariat at ipnsig.org if you have other questions. We've been working so far sort of on our own dime, and we've been expanding quite a bit lately. And there's now an opportunity for folks to be able to donate to IPNSIG in order to support events like the IPNSIG Academy and some larger meetings that we're looking to be able to host. You can scan that QR code. You can text IPNSIG to 53555, and that'll give an opportunity for you to donate. IPNSIG is a 501c3 organization in the state of California, so that can help you out. You can also become a member of the IPNSIG. We're an open organization. You can send a message to membership at ipnsig.org. The pie chart on the left is our demographics as of recently. And so we've got members from all over the world. Very happy to help anybody who's interested, again, through the library and online resources, the project's working group. There's lots of folks out there that are quite friendly who will help you get started, and we can do that. And you'll be redirected to a survey after this. You can scan this QR code to give us some feedback on how the presentation went and what you thought of it. And that's it, I think. Thank you very much.